Alrighty, so we left it off at trying to solve the issues we had with our little program, and we were trying to find why is it that they always converge, and the points always converge towards this point, so towards the points that are on the axes and the unit circle. So as this one moves, this one and this one moves, they all end up stopping here. And yeah, that's about it. Which is to say, I've got two theories. One is that I'm missing something, and the other one is that in the two-quadrant function that I designed so that I could determine where is it that the quadrant, which quadrant is in it, which quadrant is it in, I realized that, well, single precision floating point comparisons, or for that matter, just floating point comparisons in general, are likely to yield bad results, seeing how, well, if I make it equal to 0, such that I determine if we are at the top or bottom, that is O1 or O minus 1, some points will never really reach exactly 0. And so this branch is never going to be reached, except for the first time the program runs, where the points are indeed set to be be in the axes as well as the other standard positions in the unit circle. Now, a solution to this was for me to look up something about floating point numbers, and I stumbled upon this site, the Floating Point Guide, where I was basically told, at least in the basic answers section, what I already knew. And then I got into the comparison page, where apparently there's something really interesting, and that is the last section, comparing floating point values as integers. There's an alternative to heaping conceptual complexity onto such an apparently simple task. Instead of comparing a and b as real numbers, even though in my case I'm not comparing two real numbers, but rather a single one, well, I mean, I'm technically comparing two. It just so happens that one is tied to a variable and the other is just a single precision floating point literal. We can think about them as discrete steps and define the error margin as the maximum number of possible floating point values between the two values. I'm supposed to understand what that means, but I'm not sure. And I'm supposed to be reading this paper for more details. Comparing floating point numbers. So I suppose I'll read it, and I'll read, well, this one I already read. I'll read this one to see what exactly is it that I'm missing. What exactly is it that I could improve in my floating point number comparison? Either way, there is quite definitely another mistake in the way I'm doing things, and that is due to the fact that at some point as well, this point would be compared with this one. So whenever we get the position for this one, the next position is going to be this one, but not really the next position. It just so happens that you could say there's anchors. The anchor for the base position is this one. The anchor for the next position is this one, but really the next position is going to be the midpoint of the midpoint of the midpoint of the arc. And, well, eventually that will be performed in a more programmatic way through a recursive call to the compute midpoint function with a stop condition that will depend on the delta, as eventually the delta will also stop being a constant and be changed by clicking on the mouse. But for now, I have to get it working with a fixed delta and with simply 3 levels of recursiveness, even though at this point it's not so much recursiveness as nested calls. So what's going on is that this point, and this point are all converging toward this point, just as this one, and this one are all converging toward this one, and so on and so forth with the third and fourth quadrant. In the debugger, I was inspecting what exactly was going on, but so far I hadn't gotten anywhere, because right now I'm in the second iteration of, so they've already moved a tiny bit, they're going to be moving a tiny bit more, and I need to know why is it that it's sticking, why is it that they're all sticking to the axes, because it's odd, it's very odd. Yep, it's very odd. Could be it's related to the quadrant as well. There's definitely an issue with the fact, let me take note of that. Well, it's just going to be a no-go anymore. So possibly change the midpoint computation, because no, possibly change the two quadrant function to, I mean it's a static method, whatever. Possibly change the two quadrant function to perform at least more correct floating point comparison. Because the way I'm doing it now, it sucks, basically. It sucks a lot. I'm comparing this straight to, alright, is it 0? I guess as in exactly 0? Not quite. For that, I'll read this article from Bruce Dawson, recommended by the Floating Point Guide. Well, anyway, back to what we were doing. Pause, and next pause is going to be, alright, so the pause of child node 1, which has already been displaced a tiny bit at this point, is 0.83, which does make sense because it's a bit less than square root of 3 on 2, as it is, that is around at 0.86. And then it's a bit more than 0.5 for y, as well, we're a bit higher up. Then the next position is supposed to be this one, also displaced, that is 0.44 for x, as we've gone down from 1/2, and 0.89, that is a bit over square root of 3 on 2 for y, that is square root of 3 on 2 is around 0.86. Now, the opposite position, that is that for the virtual node, for this one, it's supposed to be this one, a tiny bit displaced, that is 0.89 for x, correct, and a bit less than a bit more than negative 1/2, which is to say negative 44 or so. Correct as well. Now next to p-pause is basically this one having been displaced, but before it got completely displaced to the next one. Because if I remember correctly, yeah, that's exactly how it's supposed to be. So 0.89 or so, and then 0.07 or so, which is this one tiny bit displaced in the previous iteration. This one's actually already a bit more displaced, but we always store the previous snapshot, the snapshot of how it was in each move trigger. So basically, you don't record the new the new position until all iterations have until all nodes and virtual nodes have been moved. That's when you then record again, whichever one's position you need for the next move. I don't know if I made myself clear there. Hopefully I did. Now, POP pause. Alright, so we did say that it was correct. I'm just going to continue. Midpoint should have been computed to 0.79, 0.60. So this was a bit over here, and it computed the midpoint with the one that was a bit over here. Eventually that should have yielded, makes a fair amount of sense. 0.79 is still very near to p pos, which is 0.83. Y being 0.60 also makes sense. Y was 0.55, so tiny bit of an increase. Makes sense. Now the OP midpoint should have yielded 0.93, so this one now moves a tiny bit more. So it's larger for the x and larger for the y as well. Makes a fair amount of sense. OP pos was previously 0.89 and negative 0.44. So yeah, also makes a fair amount of sense. Let's continue. Now we should be on node with ID 2. That's right. And now that we're on node with ID 2, which is this one, but position at tiny, already having displaced once, we should be getting 0.44, 0.89. That is correct. The next path should be this point having already been displaced, so negative 0.07 for x, 0.899 or so for y. That is correct as well. The OP pos should be this one having displaced a bit, so a bit over 1/2 for x, bit over negative square root of 3 on 2 for y, is negative square root of 3 on 2 is 0.86, so we're getting negative 0.83. That's right. The next OP pos should indeed be the value that we had for the OP pos of the previous node before computing its OP midpoint, which is 0.9, negative 0.44. That is correct as well. And now we can go on and move on to, well, continuing execution. Let's see what the midpoint turned out to be. Midpoints now, alright, so pos was 0.44 on x, 0.89. So around here, now it's 0.33, makes sense. A bit less for x, a bit more for y, as now y is 0.93. Makes a fair amount of sense. Opposite midpoint should be 0.60. So we were before at 0.55 for x. It does make sense that it moves along a bit more. Negative 79 makes sense because y is also larger. We're not anymore at negative 0.83 as we were here. It makes sense. Now let's continue. Now we should be at node 3, which should be this one, but it's already been displaced because it's the second iteration on the move. And we should be getting negative 0.07 and 0.99. Alright, that's correct. Next pos should be negative 0.55 and 0.83. So this is initially 0.55, 0.5, and it's already been displaced a bit as it's the second iteration. So it does make sense that x is a bit less and y is also a bit less as we're going down from positive 0.86 for the y value, for the y component. Now for the OP pos, we get that the OP pos to this one is this one. This one's already been displaced a tiny bit, so it's basically the same value, but positive x, negative y. The next OP pos should be the OP pos of the previous node. So that's right, the OP pos of the previous node was 0.55, negative 0.83, and that is indeed what we're getting for the next OP pos. So it stored the snapshot correctly of the previous node before performing the midpoint computation. That seems alright. Now, next one's gonna be p-pos, no. Next one is going to be continuing, basically. Oh, wait, I can't even write. Midpoint is going to yield negative 14 and 0.98, makes a fair amount of sense. Negative 14 for x would mean that we've moved a tiny bit more here. 0.94 means we're not at 99, we're at 94, so a tiny bit less. Let's go for x. The OP midpoint would be fundamentally the same, but with a negative y and positive x, as it's this point having displaced a tiny bit more. Makes a fair amount of sense. Now, the next node, we're already in 4. I'm just gonna skip, so let me disable the second pointer. Let me continue again, which means we should be on 5. Let me continue again. Now we should be on 0. Let me skip straight to node. So that's 0. Let me skip straight to node 2. So basically, let me continue. Now we're on node 1. Continue. Let me continue to node 2. Now we should be right now at node 2. Then it's correct. Node with ID 2. Its position was as we left it. So 0.35.93. The P next pause should be indeed the one we left, negative 0.14. 0.98 makes a fair amount of sense. The OP pause should be 0.6, negative 79, so 0.6 just moved a tiny bit more, negative 79. It's a bit over negative 8.86, which is negative square root of 3 on 2. The next OP pause should be the snapshot of the OP pause of the previous node before applying the midpoint to the opposite position, that is 0.93, negative 0.35. We didn't check it out, so I'm just going to trust it did it correctly, as I believe it's done so far in previous iterations of a loop. So dare I say, yes, that is indeed the next OP pause, seeing how this is the OP pause. The next OP pause should be this one's moved here, even though in the previous iteration, this one's already moved a tiny bit more. It makes sense, 0.93, negative 0.35, we've already got a tiny bit less, tiny bit more for y. Makes sense. Now, let me enable breakpoint 2 now. Let me continue. Let me check what the new midpoint is. So for this one, now it's at 0.27 or so. So it's likely already be at this point. And then it's 0.96. 0.96 already, we're very near 1. The OP midpoint is going to be 0.66 and negative 0.75, so makes a fair amount of sense. This has already gone a bit more, moved a tiny bit more. Negative 0.75 is going to be this one. Let me check out perhaps state OP child 2. OP child 2, right? Yeah. First state OP child 2 should now be indeed the new midpoint. Wait a second, what? Oh wait, no, that's right, yeah, because perhaps state OP child 2 stores the rotation of the position of the opposite midpoint, that is the virtual node of each node, before applying the midpoint computation. So that's right. It's basically the value that the opposite node was at before we computed its midpoint. So the new one is OP midpoint. The one we stored for the next node was the previous state OP child 2. Makes a fair amount of sense. Dare I say, let's just continue. I'm just gonna disable again breakpoint 2, and let me continue again. We should be on 3, 4, 5, 0, 1, and 2. So we're on 2 again. Let me inspect pause, just as we left it. Next pause basically moves a tiny bit more. Sorry, negative 21, negative 0.21, 0.97, so it moves a tiny bit more. That makes a fair amount of sense. OP pause should be where we left it, so 0.66, that makes a fair amount of sense. Next OP pause. I'm going to trust it's correct. But basically we can already check that. And it's basically supposed to be the reflection of this one as this one. I mean, oh boy, what am I saying? It's basically supposed to be the reflection of this one as this one's already been moved here. So basically, if we realize that that's supposed to be, well, that is how it's supposed to be, you see that it's fundamentally uh, the same as what the hell? The OP pause. We're in node 2, right? 012. Yeah. Node 2 is already at 0.27, 0.96. Next pause, negative 21.97. Makes sense. OP pause for this one is that one. Oh, yeah, sure. I was mixing things up. Yeah. Next OP pause is supposed to be 0.86, negative 0.27. Yeah. Alright, yeah. Makes sense. Yeah, makes sense. Makes a fair amount of sense. Like, let me enable now the second breakpoint again. And the midpoint is going to be 0.21, so we're approaching 0.01. I still don't know why is it converging at the axes. Very odd, but whatever. Let's keep inspecting. Midpoint turns out to be 0.21. Really, we don't care about the midpoint or anything. I think I'm just going to skip those checks. Focus on the midpoint, which is I'm inspecting why is it that, for example, this node is always converging towards this point. And once I find that out, it'll apply the same way for all of these to this one, all of these to this one, and all of these to this one. So yeah, there's that. I am led to believe it's likely related to my floating point comparisons. Quite possibly, in fact. So I'll have to work on that, but first I need a more sound proof of why is it that it's converging towards the axes. Maybe it's just infinitesimally approaching them, and that's why it never quite hits 0 or 1 or whatever it is that it's got to hit to for a program to realize, yeah, this is already hitting the axis, time to move on. Still, it wouldn't make sense. Why is it continually comparing itself with this one? It's not supposed to be comparing itself with this one. It doesn't make sense, but whatever. Alrighty. So, we've got P midpoint, we've got POP midpoint. Makes a fair amount of sense, what can I say? Next pause is where it's supposed to be. And yeah, basically. We're always at the same distance, which is nice. Alright, so let's continue the program again. I'm going to disable the breakpoint, disable the second breakpoint, just to leave this first one. Now we're going to move on to child node 3, 4, 5, 0, 1, and 2. We're on 2 again, pause just as we left it. And I'm not going to bother with OP pause, let's just focus on this one. The next one already moved to negative 28.95. Makes a fair amount of sense. Now it's time to check out what exactly is going on next, which should be let's see. Should be what now? What am I getting wrong? Not quite sure. So yeah, suppose let me go back second breakpoint. Let me move. Let me check midpoint. Midpoint should now be at 0.16, 0.98. Makes sense. Let me check. It was the opposite. Well, no need to. It's only a midpoint that I care about right now. So 0.16, 0.98 makes sense. What can I say? Yeah, suppose I'm gonna disable again second breakpoint. Let's continue execution to node 3, 4, 5, 0, 1, and 2. So again, node 2, pause just as we left it. Next pause should be negative 34, 0.93, same as we left it. There's something fishy with the next pause. How come it displays itself so little from the x-axis? That's fishy. That's really fishy. What if I access the children at position 0? No, at position 3. And I access its transform column 4, column vector 4. Great, the compiler optimized it out. I love this. Even if I issued G3, apparently the compiler still optimizes out parts of my code. There's likely something I'm not understanding when I'm compiling my code, because apparently even G3 doesn't stop it from optimizing out certain things. Oh boy. Well, without knowing that, I'm just gonna have to continue on to the next iteration after I finish checking out this child node. What can I say? Smells really fishy to me. See how the position of child node 2, which started at this point for x at 0.5, it's now at 0.34. It's now at 0.16. So it moved what? At least 0.3. So a bit over 0.3. No, actually, that does make sense. Actually, it makes a lot of sense now that I think about it. It moved around 0.34, same as this one also moved around 0.34 on the x-axis, only it's negative because it's moving counterclockwise and it started off at 1, 0. No, makes sense. Now that I think about it, it makes a fair amount of sense. So yeah, so far it doesn't seem like there's any issues. I wonder why is it converging at the axes? It's quite possibly my shitty floating point comparison when determining which quadrant does a given coordinate on a 2D plane belong to. Yep, that's possibly the case. So yeah, I'm gonna have to check again. Pause, right or not? Alright, so let me enable that second breakpoint. Let me continue again. The midpoint should now be at, makes sense, 0.12, 0.99. We're nearing 0, 1. I still don't know why this is happening, to be honest. Yeah, midpoint 0.12, 0.99. What can I say? Makes sense. Let me disable second breakpoint. Let me continue on to the next one. Position is indeed the same as we checked. Actually, let's just continue. 4th, 5th, 0, 1, 2. Let me check. I'm indeed still in node 2. I'm back to node 2. Exactly where we left off. 0.12, 0.99. Next pause. Now it's negative 41. So about the same increase. We moved from 0.16 to 0.12. We then moved from 0.99 to wait a second. I think I know what's going on. See, technically speaking, when I pass pause and next pause to this first call in the my nested compute midpoint arc, I programmed compute midpoint arc so that it considered both points and it generalized the result depending on the quadrant so that, well, sometimes I could avoid computing the actual midpoint. I mean, no, it's always computed. It just so happens that sometimes I can avoid, I really can't avoid much. That's still, in fact, let me make a note to self uh, to do if midpoint, if the midpoint computation is not modified, optimize the initial variables to only exist within the corresponding branches of the switch statement. And so, no, I don't want to optimize, no. To only be assigned, rather, be assigned to within the corresponding branches of a switch statement, as not all switch cases require the midpoint computation that is performed at the start of a function. Now back to where we were talking about. Compute midpoint arc is first determining which quadrant the next point is going to be in based on the quadrant of point B. Point B is always the next position. And the way I'm doing it is, say we emulate this case. So we passed as A, pause, and as B, next pause. I determine which quadrant B belongs to by using the two-quadrant function. The two-quadrant function gets past next pause, and it decides, alright, is Vx 0? Clearly it's not. Is Vy 0? Clearly it's not. Is Vx greater than 0? Absolutely not. So it eventually ends up in the branch of output third quadrant, which is correct. Next pause is in the next quadrant. Negative x, positive y. That is performed as you would expect. So we go down this branch to quadrant third. Within this branch, I then again switch to determine which quadrant point A, so in this case pause, belongs to. The problem here is, if it belongs to the second, it moves straight to negative 1, 0. But I don't want it to move to negative 1, 0. Because that would mean I still don't understand how come I've still not hit negative 1, 0. But I think, yeah, thing is, this worked when my delta was smaller and I only made a single compute midpoint arc. The animation was really janky, but this worked because you only have 24 possible positions. When the compute midpoint arc is computed 3 times before actually getting the midpoint, is that 24 to the power of 3 near positions? I mean, total near positions? Could be, could be. Alright, yeah. The issue is quite possible, yeah. The issue is definitely here. Here, and in my floating point comparison. So it's on the compute midpoint arc and quadrant into quadrant function. Alright, so First of all, I have to start thinking again in a bit of a more mathematical way. So let's assume we got past a, this point, 1, 0, b squared of 3 on 2, 1/2. Having get past that point, because it's always an infinitesimal approach, we don't want to rely on things like always getting it at a certain point. We want it. This is actually really interesting. So we always want it to perform the computation, right? That's right. You bet your ass, that's right, motherfucker. Sorry for that, I didn't mean to. Alright. I can guess how we'll never quite get to 1, 0, but by adding the unit difference, which was the difference between the unit radius and the hypotenuse of the midpoint in the straight line that is formed between A and B, gets you to the point. Now, say I'm computing 3 times the midpoint, so you get it there. Which is to say, even if we are in the fourth, so if it started out at right, at first, or at fourth, we would need it to always perform this computation. That is my theory. And so this is getting away. We're moving this here. And then same applies to this. Same goes for this. So this goes away. And yeah, there I say, that's about it, right? And for example, these branches, we only ever hit them once. Or at least I think so, because we won't ever really get to 1, 0, 0, 1, negative 1, 0, or 0, negative 1. Again, we will always get approximations, but never quite there. Let me try out the code this way. So let me disable them all. Let me continue execution. Why is this like this? What the hell? Let me quit. Alrighty. And we should be capable of getting, well, we deinitialized what had to be deinitialized. Oh, god damn it. God damn it. We quit. Let me make again. Let me just make it clean. Make. Let's see how the program. Oof. Alright, let me increase the delta so I see. One should make it a bit smoother. Yeah, they always end up converging. I don't like this. Now I understand things even less so than I did. Oh, Lord. Alright. what could it be that I am missing in some major ways? Dare I say I still don't know. Switch quadrant to quadrant, right? I'm going to the quadrant first. So if it determines it to be on the first quadrant, it then switches A. Whether it is, it doesn't really matter where is it. You just compute the midpoint, you add the unit difference, and yeah. Even if we're coming from the fourth, so even if it's at this spot, some point there, it's still converging always to point. Why is that the case, dude? Thing is, point, it's not supposed to. And I'm not sure why is that happening. So I'm getting so I'm checking. If B is anywhere here, we make it so that if B is at any point here that is not on the axis, we take our midpoint computation. But it's not necessarily plus the unit difference. That's the thing. Say it's at the fourth here and B is here. The midpoint is not necessarily going to end up. How the hell do I determine that? Because the midpoint could be negative. Like, I get the midpoint from that point to that point, and I get it there. Then I go from this one to this one, and I get there. And then from this one to this one, and maybe it's a bit negative. But if at this point this is first quadrant, I already determined, hey, you're going to end up being positive. Because I add to the midpoint x the unit difference, and I add to the midpoint y the unit difference. But it could be that it's not. So what exactly is it that I'm supposed to do to correctly identify whether I should provide negative or positive signs, directions. Not directions, we're only considering points. To the computed midpoint. Because dare I say, that is the issue. That is indeed the issue. Yeah. 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 It's going to be a bit of a problem right there. What if I don't rely on switching the quadrants? What if I try to, alright, so I compute the midpoint. Say I have a midpoint between this one and this one. Or rather, between some point that ended up here and some other point that ended up here. So we compute the midpoint and get that one, and then possibly it ends up at the first quadrant, not at the second, even though the B was at the second. And according to my computation, that means it will eventually move on to the second. So yeah, there's a bit of an inducing behavior there. Not quite exactly what I need. And that's all because when I compute the midpoint, I always compute with the absolute values of the x and y components of the vectors that I pass. Really, there's two-dimensional vectors, which in this case only apply as points in 2D plane and the 2D coordinate system. So technically speaking, the midpoint formula applies regardless of whether we're computing absolute values, right? So it's all about just adding them together, getting the midpoint, and that's it, right? Let me assume I'm on the second quadrant. So let's say the midpoint turned out to be around here. No, let's make it known so that it's easier to simulate the behavior. Let's say the midpoint turned out to be this one, so -1/2 square root of 3 on 2. Without the absolute value, of course. When I compute the unit difference, then I go 1 minus the square root So maybe what I need to determine is not the quadrants. I'm not to determine this. This is actually interesting and it could provide accurate results. What if instead of determining the quadrants of the vectors that I provide, which doesn't necessarily yield the right quadrant for the midpoint, I compute the midpoint without using the absolute values. Then I determine the quadrant of the midpoint, and that is what is going to yield whether I should add or subtract the unit difference to get its projection on the actual circumference and not just on the line that joins and not just on the equation of a line that joins points A and B. So let's go ahead and try it out. So let me go ahead, get rid of this, get rid of this. This should simplify the computation. Then we're going to go switch. This is going to be quadrant to quadrant, and I provide the midpoint. And I say, alrighty, are we at the top? Oh boy. Are we at the bottom? Are we at the top, bottom, left, right? So left, case, bottom, no, right, what the fuck am I saying? Right, what the hell? We break, or we are on the first, on the second, on the third, or on the fourth. Now say we're on the top. If it turned out to be on the top, thing is, I know it's never going to be on the top. It's just never going to be on the top. There's no way a single one of those nested midpoints computations yields exactly 1, 0, 0, 1, negative 1, 0, or 0, negative 1. Absolutely not. So let's assume initially that we only consider those, and then let's make a default case. So default break. And then let's take all of this and comment it out. Alrighty. So, unit difference, my friend. If it turned out to be on the first quadrant, the midpoint, then we're going to go ahead and say, my friend, we are going to return midpoint is going to be positive, well, no need to. Midpoint x plus unit difference, midpoint y plus unit difference. Now, if we are on the second quadrant, oh brother, what the hell did I just do? Midpoint x is going to have the unit difference subtracted. Midpoint y is going to have, what the hell did I just write there? The unit difference added. A third quadrant is going to be negative for both. Midpoint x minus the unit difference, midpoint y minus the unit difference. Then we're going to have midpoint x on the first quadrant plus the unit difference, and midpoint y minus the unit difference. And dare I say that's about it. I think to make the unit difference, I am going to have to get the absolute values of the midpoint though. So let me get that, let me wrap it in a GLM apps. I mean, my lord, the hell did I just do there? And I think this should get me the right results, but it's all very much experimental and not based on sound logic, just a hint. Still, a hint could lead me to the right results. So maybe it's correct and maybe it's not, but let's cross fingers and say maybe this is the thing that will save me from further desperation and possibly teach me a few things about geometry. So this is an absolutely completely ruinous result, because what the hell is this? What the hell is this? They're not converging, but they're not quite. Oh, brother. So they are converging. Alright, I'm gonna have to go to the bath, and I'll be back in a second. Oh boy. Claro, papi, tengo trabajo. Alrighty, we're back at it. So, after having thought it through, I don't know what's going on. I genuinely don't have the slightest idea what's going on. It's supposed to yield the correct values, which would be the midpoint with a full-on sign, then the unit difference, which is basically taking the difference of the whole radius minus the square root, then determining quadrant of the midpoint. The unit difference would basically use the Pythagorean theorem, so basically a squared plus b squared is c squared, where c squared is our unit difference. Where c squared is this, is basically this, where c squared is this, the square root of the midpoint x to the power of 2, midpoint y to the power of 2. Of course, I've got to take the absolute values of both midpoint x and midpoint y, such that I get a positive distance, basically. That's get me the hypotenuse. I will subtract to the radius, which is always 1 for our abstraction of the unit circle. That should get me a small additional I still don't quite understand why is it that it's not quite there. If the midpoint turned out to be on the first quadrant, then you simply end up with, well, that. And then, clearly this is a better way of doing it, and I can get rid of all of this massive switch statement that really wasn't correct. So we compute the midpoint, say, this point and this one yields this one, and that technically should be correct, I suppose. Yeah. I get the midpoint again, and then the unit difference is basically, well, the midpoint has its own x and y components, and the x and y components make the a and b values of the standard a squared plus b squared equals c squared, where c squared is the hypotenuse. So our a squared, our a, which is, well, this is our a, is the midpoint x. Our b is the midpoint y. Technically speaking, what we end up with is yeah. Yeah, we have the length of our triangle. So we have the length of our triangle, that is, we then square them. We square the lengths. And that's what I do. I square the lengths by first getting the absolute value of those certain midpoints. So I get the length squared, I get the length squared. I add them together. And upon adding them together, I compute the square root so that I get a hypotenuse. And yet, I'm going to have to put in a breakpoint here because it clearly doesn't work. Indeed, it doesn't work. Let me set the delta to something like 0.1. And they'll end up converging again. Quite beautiful. Exactly, yeah. Basically, I had to set breakpoints. Alright, so let's set a breakpoint at 464 and another one at 482. So just on the return statement. Let's run. And let's print first midpoint. The first midpoint ends up at 0.903.25, makes a fair amount of sense, seeing how it's going to be half of this and half of this around here. Can I call the function so that I can first, that is correct. And so on the first, the unit difference is going to be, well, I mean, technically speaking, isn't the unit difference always going to be, well, maybe not always. I mean, maybe there's a chance. Could it be that it's because of that? Nah, no. We need the point projected on the plane for every single midpoint arc computation. The midpoint arc ends up being at 0.03, 0.25, so basically you just add 0.03 to both of those components so that you actually get the point in the plane. Let me quickly open up GeoGebra so that I can, let's see. Let's set a point at 0.93. I mean, how did I get a circle? Well, I think circle with center through point, circle with center radius. What if I do this? So radius gonna be unit length. So 1. Let me go zoom. No, Lord, my Lord, no. Undo. That's right. No, God damn it, no. Let me remove that one. What the hell is that? Let me delete that one. Let me make a point right there. It's gonna have radius 1. God damn it. Oh my god. Delete. or use 1. There we go. How do I move, brother? I forgot about using GeoGebra, bro. Oh, there we go. Alright, so at 0, 1, if we then plot a point, and I set it at sort of 0, so what did I get there? 0.03, so let's go with 0.93 and 0.03. How the hell is that the midpoint? Oh yeah, dumb. I'm so fucking dumb. It's 0.25, yeah, of course. Makes a fair amount of sense. So there's that. Now if I take and I make 0.93 plus the unit difference, so 0.03, and then 0.25 plus 0.03, we get it on the circle, as we can clearly see. And so that one is actually projected on the circle, which is nice. It's really nice, except wait a second. If I make a line that goes through this point, I mean, that's not quite. Now that I think about it, that is not a good logic. It's not accurate at all. Yes, indeed, it's not accurate at all. Alright. I can think of another way of solving the problem. If I get the equation of the line, for the line that goes from 0, 0 to the point we just computed, I can then compute the point that is some amount after that. Alright, so the unit difference is an issue. That is not a correct unit difference. That is not its projection. Because if I set a point at, so this is going to be 1, 0, and I set another point at 0, 1, so 0, no, I set another point at square root of 3 and 2, so SQRT of 3, god damn it, SQRT of 3 on 2, why is it that this thing doesn't let me get, you're at 1/2, and we're going to add another point, that is going to be at 1/2 SQRT of 3 on 2. And we're going to make a line that goes through E and D. Well, we don't need to. Basically, just so I improve this point is supposed to be E dot X plus E dot Y, or rather, E dot X plus E dot Y divided 2. What do you mean, brother? Oh my god, alright. Let's get rid of this one. And let's keep that one. We got that one, we got that one. Let me move this one back up here. Can I not move it? Whatever. Let's delete this one. Can I refer to like E, X, E, Y? What the hell? No, that's not what I want. What I want is dx plus EX divided 2. Then I want dy plus EY divided 2. But dare I say, that is not recognized as correct. So, yeah, manually it is. Maybe it doesn't recognize subscripts. It's supposed to be dy and then dey. But probably that is not a good. So yeah. Alrighty then. So basically I'm just gonna have to take 1 plus square root of 3 and 2 divided 2 plus dy, which is 0, plus 1/2. And we get the point, 0.93, 0.25 approximately. Now, if I get the hypotenuse from point A to point B, we are cooked, to say the least. Absolutely cooked. Because the line from A to B, taking the length of the line from A to B, and taking the radius of the unit length, which is basically 1, and subtracting the hypotenuse yields an amount that is not necessarily the one. Right. The problem is the unit difference is wrong. That is, I don't know if that is the problem, but it is a problem. If I were to then compute the goddamn it, the um if I were to compute now the hypotenuse for the y component, I'd be getting some line that goes, so a line that goes there. The problem is getting a line that goes from A to B gets me the hypotenuse. So basically I have to take what is this? Parallel, perpendicular, polar, best fit, polygon, semicircle, circular arc, angle, area, reflect, translate, slider, move graphics, Uh, if I get this point, so if I'm supposed to get this point, we end up at 0.97. I mean, it's supposed to be the intersect of f and whatever the hell it is that 2 is. 2 being the circle and f. How the hell do I compute this? Clearly the idea is there. Now I only need to know how do I compute the intersection of the line that goes from the origin to the point to the midpoint and intersects with the unit circle. At the intersection with the unit circle, and there's a problem there, because it intersects with the unit circle also here, but that's the third quadrant. So I'm going to have to get the intersection and give it the same signs as the point here, as this point. All right, so I'm going to have to interpret the quadrant of the midpoint and then get the intersection and give it the same signs as the midpoint. Now, GeoGebra, you wouldn't happen to, be capable of providing me with a definition for this intersect function you're using here? No, right? That's what I thought. That's what I thought. Maybe there's something here, definition and value, description, definition. Nope. Description. Nope. Definition and value. There is a problem, a pretty big problem. And clearly the way I was doing it, it's not correct. Because, see, B here, whatever you had to add to its x component and its y component, clearly the x component is larger than a y component. But the way I was doing it is adding the same thing to the x and y, and so it ends up not quite at the midpoint. And that probably ends up adding up such that the results end up a complete piece of absolute garbage. Which is to say, my process to compute the midpoint arc is, then again for the third time, wrong. Actually, this is the fourth time I changed the way the midpoint is computed. But at least now I know what I gotta do is get the equation of a line between point B and the origin, and then compute the intersection between that equation, and that line, and the unit circle. It'd be great if GeoGebra could provide me with a definition for that, but much to my unfortune, I am left to yeah, you wouldn't happen to have definitions, right? Unfortunate thing. Uh, yep, quite the unfortunate thing. What with the two, though? Two seems to be something about the intersect. Maybe two is supposed to yield the second intersect, considering the first intersect is the one that's got the smallest values, and it's this one. So if I were to put 1, indeed it'd be that one. Alright, yeah. It's because it takes the intersect, and then it takes the third parameter is which one of the two intersects do you want to take? Alright, yeah. Nice. Here. And because there's only 2, it only accepts 1 and 2 anymore. Just yields unknown results. Alright, fair. Now, can you please give me the intersect? Please, Lord. Let's see if Wumbo has some formula for the intersect. So Wumbo, let's just look for intersect and see if they get something. Clearly there's nothing that I'm interested in because derive point between 2 lines. Technically the 2 lines are to be given in that form, but I, much to my own misfortune, cannot say I know the equation of that one. The equation of the circle is x squared plus y squared equals 1, but that's going to be a problem, a bit of a big problem. So clearly this turned out to be wrong, this turned out to be correct, but now I need to find out how do I compute the intersect. So let's just go ahead and look up GeoGebra functions docs. Surely they have documentation, right? Let's see. Commands. So function commands, intersect, yields the intersection points of 2 objects. And it's specifically using the second overload for intersect, which takes an object, another object, and the index of the intersection. So if there's more than one, it accepts an index. Yields the nth intersection point of 2 objects. Each object must be a line, conic, polynomial function, or implicit curve. Can you provide me with the implementation? Because I'd like to know how you implemented this intersect, as I need it myself. Let a of x be x cubed plus x squared minus x, be a function, and b be another function. The intersect yields the intersection point of a function. You wouldn't happen to, not good, maybe in the resources. So, is this algebra? I don't have the slightest idea. Maybe this is geometry. What do you have for me? Let me just look up intersect and see what it's got for me. It is what I need. Circle intersect with straight line. Alright, but can you please provide me with the implementation or a formula that I can think about to implement? Alright, this is all nice, but change the radius, sure, whatever. We know the equation, but I don't know how to get the midpoint, the intersection. So please, can somebody give me a formula for the intersection of a circle to compute all intersections of a circle and a straight line? Circle intersect with straight line algorithm. That's it. I gotta find something. Circle line intersection algorithm for competitive programming. So, given the coordinates of a center of a circle and its radius and the equation of a line, you're required to find the points of intersection. My God. Solution. Instead of solving the systematic equation, we will approach the problem geometrically. This way we get a more accurate solution from the point of view of numerical stability. We assume without law of generality that the circle is centered at the origin. If it's not, we translate it there and correct the c constant in the line equation. Alrighty. By C constant, do they mean the B constant as in y equals mx plus b, only they call it C? Or am I misunderstanding? Whatever. So you have circle at radius r and a line with equation ax plus by plus c. In our case, we have an equation negative 0.25x plus 93y plus 0 for c, the constant, equals 0. Let's start by finding the point on the line which is closest to the origin. First, it has to be at a distance d0, which is the absolute value of our constant, in this case 0, divided whatever, which is going to be 0. Second, since the vector AB is perpendicular to the line. Now, the vector AB is perpendicular to the line? What the hell? Vector AB is given by the quotients of the line equation on the x and y components. So, it's the coordinates of the point must be proportional to the coordinates of this vector. So let me think about that one. I'm guessing, yeah. So let me think about that one. We have our line. All right. And since the vector, all right, so we start by finding the position on the line which is closest to the origin. It has to be a distance d0. The thing is, our constant is 0 as well. So the point at which crosses the x-axis is 0 itself, in and of itself. Which is to say, taking the absolute value of c would yield 0 in our case, and it would be distance 0. The point on the line which is closest to the origin. The point on the line which is closest is 0 itself because it crosses the origin. Second, since the vector AB is perpendicular to the line, except it's not, right? The coordinates of the point must be proportional to the coordinates of this vector. Since we know the distance of the vector AB is perpendicular to the line, I don't quite get that one. The line being ax plus by plus c. The vector AB, I mean, what the hell are you expecting me to believe there, bruh? Vector AB, if we assume vector AB to be, do they mean that the base of the vector is B? In which case, yes, but not necessarily. We don't know the direction of the vector. No, they quite possibly don't mean that. They mean the vector has base 0, 0, but that's not perpendicular. It's parallel. And in fact, it's laid out over the line, right? In our case. Since the vector AB is perpendicular, let's continue reading. The coordinates of the point must be proportional to the coordinates of this vector. Since we know the distance of the point to the origin, no, we don't know the distance of a point to the origin. We just need to scale the vector AB to this length, and we'll get, except vector AB, it's 0. Brother, x is 0, y is 0 is 0. 0, my friend, 0. The minus sign are not obvious, but they can be easily verified by substituting x0 and y0 in the equation of the line. Alright. At this stage, we can determine the number of intersection points and even find the solution when there is 1 or 0 points. Indeed, if the distance from x0, y0 to the origin d0 is greater than the radius r, the answer is 0 points. Let me reread that one. At this stage, we can determine the number of intersection points, and even find the solution when there is 1 or 0 points. Indeed, if the distance from x0, y0 to the origin d0 is greater than the radius, the answer is 0 points, which it is not. If d0 is r, the answer is 1 point, which it is not. If d0 is less than r, which it is, because d0 is 0 in our case, and r is 1, well, there are 2 points of intersection, which indeed makes sense. And now we have to find their coordinates. So we know that the point x0, y0 is inside the circle. And by the way, it's 0, because if you're multiplying by constant c and our constant c is 0, it's going to end up 0, 0 anyway. The 2 points of intersection, ax, ay, and bx, by, must belong to the line ax, by plus c equals 0. Correct? It must be the same distance d, and that's the part that we, oh wait, it's d, not z0. So yeah, it's some distance d that we're introducing just now from x0, y0. Correct as well. And they're both at the same distance, yeah, figures. And this distance is easy to find. And that's a distance I don't seem to be quite capable of finding. But still, from x0, y0, our x0, y0 is 0. And the distance is easy to find. So I take the square root of the radius squared minus 0, which is going to be 1. Our constant c is 0, so it's going to be 1. And so we take radius squared, 0 is going to be 1. Distance is going to be 1. That is obvious, because it's not the circumference. It's obvious at 1. So what else do we have? Note that the vector negative BA is collinear to the line. So if it's collinear, it's in the same line. And thus we can find the points in question by adding and subtracting vector negative BA scaled to the length d to the point xo, 0, xo, yo. The equations of the 2 points of intersection are, so the distance squared, which is 1, gets us m being, well, the slope and thus the scaling of the vector. And so we go ax is x0 being, well, 0, plus, and b being b are what we needed. So if we compute in our case a squared plus b squared, we know that a squared b squared is the line given by negative 0.25 and positive 0.93. The problem now being, how do I realize that it's negative 0.25 and positive 93? Because that is already assumed to be part of the input data set, but what I have is positive 0.25 and positive 0.93, which is not good, basically. Still, I can get it in y equal mx plus b and then pass it to this form, which I forgot the name of, but yeah. Alright, so let's take note of the process. The process is supposed to be modify the compute midpoint arc function to perform the following steps. Number 1 being compute the midpoint between given vectors, given points in this case, which is already done. Number 2, compute the equation of the line between 0, 0 and the midpoint. This would mean getting it in the form. So for this, get the equation, get the parametric. Wait, no, it's not the parametric. Damn, I forgot the names. Holy shit. Get the equation of the form y equals mx plus b, where b equals 0, m equals whatever the hell is supposed, and where equal, and solve for m. Second, transform the equation to the parametric form. Ax plus by plus 0 plus c equals 0, where c equals 0. And then third step is going to be, once we have the parametric equation, we can proceed with the actual steps that it mentions here, which is, well, in our case, it's always gonna, we're always gonna have the invariant that b0 is 0, x0, y0 is 0, 0. The distance is 1, and so we have to compute m, and well, this is really what we need. So once we have the parametric equation, we can just move on here and go compute the scaling to the vector negative ba, where b and a are parameters to x and y in the equation obtained above. Step 4, compute the final, compute the projection of the, I mean technically the projection, but not quite. The midpoint of, compute the midpoint, no, yeah, compute the intersection of the equation, of the line rather, with the unit circle through for some point ax by, but I better give it another name. Let's go just bxy, and that is where we go and I go m is going to be the square root of, well, in our case 1 divided, and this is where we get a squared plus b squared, and let me parenthesize that. Then to compute the intersection of a line with the unit circles for some point xy, we're going to take the scaling factor and we're going to say, all right, our point x is going to be what? Oh yeah, because we have two intersections. Problem being, which one is it? No, basically, then I can just determine the quadrant of them, and whichever one has the same quadrant as the original midpoint is the one that we're going to return as the genuine midpoint that we're interested in. So yeah, it's actually going to be for some points x1, y1, and x2, y2. So for x1, I'd be going, well, 0, which in our case is always going to be 0. And it's going to be b plus b times n, so b times n. Then y1 is going to be minus a times m. So negative a times m. The other intersection is going to be negative b times m, and y2 is going to be a times m. All right. Had we solved the original systems, we would like to get an answer in a different form with a larger errors. Geometric method described here is more graphic and reaction. Alrighty. Well, I think this should get me what I need. The only thing that I have to make sure of is that I can go from y equals mx plus b to the ax plus by plus c. Alright, so first we have the midpoint, which is already done. Compute the equation of a line, which is going to be first getting the equation of the form y equals mx plus b. Basically, we have to solve m. Also, better idea that I call this s. Better idea, yeah, that I call this s as the sort of scaling factor, even though it's, yeah. Now, when I transform the equation to the parametric form ax plus by plus c, where c equals 0. Now, I'm going to have to first get this. This should be fairly simple. We know that the intersection with the x-axis is at 0. At x equals 0, we do have some point, the point being the midpoint we just computed, so I can use and solve for m, where b equals 0 and xy equals the midpoint, basically. And yeah. Alright, so b equals 0 and xy are the midpoints. Then we get the slope, and then we get the actual formula. Then I have to get the equation in parametric form, which is really just taking the same factors that we got, but assigning the right signs, which is the part that I can't quite get right. So, obtaining the parametric form of the equation of a line. I forgot how to do that, much to my unfortunate. Equations of lines from poles on line magnets. Sure. The info I need is probably here, but I'm gonna ignore the idea that it is here. And yeah. Let me see if Wumbo's got something. So, parametric. Beautiful. So, we can use the concept of vectors and points to find equations for arbitrary lines in the realm of real numbers in dimensions, though we will focus on 3 dimensions. To begin, consider the case n equals 1, so single dimension. There is only one line, which is here, which is familiar with the number line, that is r itself. Therefore, it is not necessary to explore the case of n equals 1. Alright, now we consider the case for where n equals 2, in other words, r2. P and P0 will be 2 different points in R2, which are contained on a line L. P and P0 will be the position of vectors for the points P and P0 respectively. Sure. Alright. Suppose that Q is an arbitrary point on L. We're going to be able to define Q in terms of P and P prime. And P0. Consider the vector P0P, that is P minus P0, which has its tail at P0 and point at P. If we add P minus P0 vectors to the position vector P0, for P0, the sum would be a vector with its point at P. Fair? Now suppose we were to add some t function with input P minus P0, where P is to P, where T is some scalar. Oh wait, no, it's not a function. Alright, so T is some scalar. You can see that by doing so, we would find a vector with its point at Q. So apparently I got the parametric description of the line wrong. Oh boy. I'm gonna have to look up the types of equations of a line because I forgot. Equations of lines in different forms. The slope-intercept form, the point-slope form, the equation of a vertical line, the equation of a horizontal line, the general equation of a line. That's the one we need. Alrighty, that's the one we need. Technically speaking, we do have some factors a and b, but we don't have the signs for them. Such is the case that yes, basically. I do have the slopes. Alrighty. This is probably so much easier than I'm making it out to be. The slope-intercept form. Sure. B is the y-intercept. The hell? There's a point where it cuts with the x. Right? Alright, so the general equation of a line in a two-dimensional xy plane. Sure. Sure. Because the given equation y plus 2x equals 1 has two variables x and y, it has an infinite number of ordered pair solutions that may be found by giving a value to one of the two variables and find the value of the second variable. That is, it has two variables, it has an infinite number of ordered pairs. Problem being, what if I don't know? My lord, bit of a problem we got there. It's minus 0.25 and positive 93 for a reason yet unbeknownst to me. And of course, C is 0, crosses the origin. The problem being, how could it be that, like, bit of a problem. Let's see. Find general equation of a line through, find the general equation of a line through given a point. Given a point on a line. From, I mean, that is alright, but not quite. So say we have A and say we have B. I mean, you can compute the point slope formula. Yeah, what can I say? you get the slope, the point slope formula. Um, the slope intercept. But what if you wanted just the goddamn, oh Lord. What if I just want the the slope or gradient from 2 points? It's just so simple, and I forgot about a lot of things about geometry, so I am cooked. Oh, brother. Um, so the equation of the form of that, and it's not the parametric form, it's general equation to the general form where c equals 0. Problem being, we don't know what ax and by a is supposed to be, nor do I know what b is supposed to be. So I am led to believe it could be that it's ya, so 0 minus. Say I got rid of the signs here. My lord. Say I did 0.25x plus 0.93y equals 0. If I did that, I'd be getting, let's say I did this, and then I did. Yeah, I think I get it. So basically, for some point, to get the general equation, I'm going to have to, this is very rudimentary, but it is what it is. Initially, I could be led to believe that both are positive, and I simply have to exchange the x and y values, but then you get you don't get the right, basically. Now, say I had negative 0.29. Say I used negative y. Turns out to be on the same plane. I mean, it seems fair. Now, if I were to compute, let's say, so technically, on the first quadrant, one of them both has to be negative. Maybe? That's an invariant. That's an invariant. Say the midpoint is now here. So it's technically 0.93x, I mean negative 0.93x. And then, so really the absolute value would be 0.93 and 0.25. So I reverse 0.93 and I put negative 93. But then I have to make the y value positive, oddly enough. Now let's say, so I can say that, let's take note of that. If the midpoint is in the first quadrant, then a equals y and b equals negative x, as we see here. Yeah, it's laid out right over here. Yeah. So I exchange the values and I negate
that one. Now, if midpoint is in the second quadrant, then A equals negative y, B equals x, apparently. Because if, say, we have negative 93, positive 25, I'm supposed to end up with an equation of the line that exchanges y, so y would be the same, and b would be the same, except not. B is also negative x. So because technically at this point it would be negative 93, positive 25. So positive 25 is now A, and then negative 93 is positive 93. I think the pattern is repeated, right? Now, if the midpoint is in the third quadrant, then A equals, good question. If the midpoint, say, is at this point, so it's what? 0.25x, negative 93y. So I exchange the y and I add, so it's going to be negative. So if it's on the first quadrant and I got negative x, so negative 25x, negative 93y. If it's in the first quadrant, it's going to have to be negative y, b equals x. Because technically it's going to be then it's basically going to be b is negative 25, so you leave it b, but x is negative 93, and that's why you have to go negative 93 to get positive 93. Then if I'm on the fourth quadrant, if the midpoint is in the fourth quadrant, then A is supposed to be what's it supposed to be? So say I've got my midpoint here in the fourth quadrant, and I got positive 93, negative 25. We can exchange them, but then it has to be positive. And then technically it's the same intersect as this one, but you're supposed to take this one's intersect. It's actually, yeah, well, I suppose it is what it is. It is what it is. And then whatever point is supposed to be, it is. So if we're on the fourth quadrant, so x is positive, y is negative. If it's in the fourth quadrant, then we're supposed to get negative y. So if that is positive 0.9, negative 0.25, then A takes positive 0.25, so minus 25, and B takes positive 93. I can see a pattern there, and I could probably think of something, but for now, Let's get it done this way. The less mathematical way in this particular instance. All right, so we got a midpoint, which is correct. This is not correct at all, and for that matter, none of this is. So may as well start from scratch. We're gonna start with an auto. That's gonna be basically I'm gonna need if I get the equation of the line, we can compute the scaling, but basically what I need is the factors of the equation of the line, because those are the ones that I then use for both the scaling factor and finally to get the points. So what I really need is first, I mean, do I really need, I don't need to get in the form, yeah. Now that I think about it, I don't need this step. Yep. So simply I just, we got A, B, and C. So this is where I'm supposed to get auto. It's going to be general A. We're going to call it general A. Well, rather than auto, it's going to be, there's going to be a float, and then we're going to have a general B. Then I'm supposed to go ahead, switch the quadrant in which the width point is. If it's the first, something. If it's the second, something. If it's the third, come on. If it's the third, something. If it's the fourth, something. And if it's anything else, something else. If it's the first, I'm going to go ahead and say, yeah, the process was, if the midpoint is in the first quadrant, then we know that general A is going to be midpoint Y. General B is going to be midpoint X, but negative midpoint X. If it's on the second, it's going to be, well, we can actually generalize this and say this is, if it's on the first or the second, this one. If it's on the third or on the fourth, this one. We can get rid of that one, get rid of that one. General A is going to be negative midpoint Y. General B is going to be regular midpoint X. Now once we have that, we can go ahead and say, I'm going to compute the scaling factor, so it's going to be right over here. Wait, I wouldn't be happy. Yeah, I'm running the program, god damn it. Alright, let me BR disable all. Let me continue execution. And let me exit out of this. Let me go back here. Let me go float. It's going to be the scaling factor, so I'm going to go glm sqrt. And I'm going to go ahead and do 1f divided general A plus general B. So, no, what am I saying? glm pow of A to F plus GLM POW of B, so general B to F and this is, oh, sorry. This is supposed to be scaling. What the fuck am I doing here, brother? And I was supposed to get the scaling there. Then we may as well make it const. Once I have the scaling, I can go ahead and compute the final points. So midpoint x, or rather, whether it is x1, y1 or x2, y2 is going to depend on the quadrant of the midpoint. So if it's on the first, no, it's going to depend on whichever one of the 2 points is in the same quadrant at the midpoint, yeah. So yeah, let me take note of that. Take the point that is in the same quadrant as the midpoint initially considered. Now here is where I'm supposed to go ahead and do compute x1 and y1, then compute x2, y2. So we're going to go const y1 is going to be, I mean, we could just make it a gln vec2 and say p1 and then p2. Now its x component is going to be general B times scaling, and its y component is going to be negative general A times scaling. Second point is going to be negative general B times scaling, and general A times scaling. Then I'm going to go ahead and switch the quadrant of P1. So, yep, I'm going to get the quadrant of P1. And I'm going to go ahead and say, or rather, this is simpler. If quadrant to quadrant of P1 is equal to the I'm going to have to store the quadrant. So let's just call it quadrant. Let's go here and let's do const quadrant type. It's going to be the midpoint quadrant. And it's going to be initialized to the quadrant of the midpoint. Then we're going to use it here and go and do midpoint quadrant. Then we're going to go here. If it's equal to the midpoint quadrant of this one, then midpoint is going to be P1. Else if quadrant to quadrant for P2 is the midpoint quadrant. And if none of that is that, then for now, we're just going to make a throw logic error. No quadrant aligns. No computed point aligns
with a target quadrant. Now, this is going to be this way, and we're going to return the midpoint. Alright. Now that that is done, let's quit out of here. And let's see. Let me review. Oh boy, what the hell did I just do? Alright, so once we have a possible point, this is all about checking then whether the quadrant of that point is the same as the midpoint's quadrant. There's a midpoint. If it is, it's that one. The computed point aligns with the target quadrant. In the circumference. So, we're going to compute the midpoint arc. Takes those two vectors, which are the ones that delimit the arc. We first compute the midpoint in the straight line that exists between the points on the arc. Then I get the quadrant of the midpoint. Then I get some general, the general equation is A factor, general is B factor. If the midpoint quadrant ends up being on the first or second, general A is going to be midpoint Y, general B is going to be negative midpoint X. For the third and fourth is going to be a negative midpoint Y, positive midpoint X. Then, anything else, you can break. Though ideally, let me throw as well. Some target quadrant was not considered. And hope that never throws. If it works, I'll get rid of the exceptions, but for now I need them. Then we compute the two possible intersections with the circle that the line has. And once I've computed the intersections, I check if they align, which one of those points that intersect with the circle are in the same quadrant as the midpoint quadrant. Whichever one is in the same quadrant is going to be, well, the right one. I hope indeed. Yeah, let's run it. Well, it works. Hell yeah. Finally, it works. My lord, finally it works. We got our wheel. It took me 2 days, but I got it working. Well, not 2 days, a day and a half. Less than a day and a half. Well, great. We got the wheel working, and what a nice and smooth animation we got right there. Now it's time to let the user control the speed of the wheel based on how many times they may perform right clicks to speed it up, or how many times they perform left clicks to speed it down. Alrighty, well, it works. That makes me happy, and it also means I have to document this function to get rid of that to-do comment. So, unfortunately, I'm going to have to document it in Spanish, so there's that. Alright.
Mm. All right. So it's documented. I still have to document this function, which is basically Then I take note. This one is useful less anymore, and this one is still. This is supposed to be done, and this one as well. So those are those two to-do lists that I need. So yeah. Alrighty. Now I can get rid of this one. And let me compile again, see I didn't miss anything. Nice. And now comes making the animation itself be still smooth, but allow changing the speed at which it goes. So as I was writing the documentation, I was also thinking about that, and I realized that I can technically go ahead. What is that? What the hell? I can technically go ahead and assume that the faster it goes, the less midpoints I'm going to have to compute. So the less times I'm going to have to recursively compute the midpoint. Yes, of course, I'm going to have to need another function that gets past the stop condition for the amount of stack frame allocations I make on the recursive calls to the compute midpoint. And the relation is actually directly proportional, as the less time we set as the delta, the less midpoint computances we have to consider, because the more times we have to animate, that is, the smaller the delta, the less times the user has to check that, hey, the midpoint is actually not, we get that, hey, we're getting a larger or smaller increase on the midpoint. So let me try it out with only the first call. Yeah, of course. And let me try it out. It should not look too janky though. A bit janky, but not too janky. It's fast as fuck, basically. Yeah. Maybe if I continually keep increasing. So I'm going to need a new function that recursively computes the midpoint arc. Or technically, I could leave the delta to be the same, and the clicks only determine how nested is the recursive computation of the midpoint arc. That is, the more clicks we make, the less computations we have of the midpoint arc until we reach only a single one, as we did now, and it's going fast as fuck. The more clicks, the more left clicks, which means slowing down, we make, the more midpoint arcs we compute. That is, the smaller the increase in the midpoint arc that we compute. Dare I say, it seems like a fair thing, but I want to try it out by, of course, making a function that lets me do that. So it's supposed to return the final, so it's going to be recurse midpoint, and of course it's going to need the initial vectors, which are the vectors for the midpoint computation, and what the hell am I doing? Const vec2, and then it's also going to need the stop condition, which is going to, of course, be different depending on the speed. All right. The speed will determine the amount of nesting. So, yeah. The nesting level is going to be, what's the speed it's giving it? It's using a float, but I'm gonna assume it's an integer. So let's go with int. Now we can go here and do recurse. Let me copy this. Let me go here. Let me replace this, and let me make this A. Let me make this B, and the way this should work is going to be a tiny bit hard. At least I think it's going to be a tiny bit hard. But recurse midpoint is basically going to call the midpoint as many times as int. So really we don't have to recurse. We can just do it iteratively. We already know how many times we're supposed to iterate based on the integer we got past. So speed, or rather recursions. It's not a recursion, but whatever. All right. So I'm going to go ahead and do, we're going to need the final vectors. So the final midpoint, right? Yep, dare I say. And here we're going to go for auto I 0, so long as I is less than recursions we add to I, and basically here I'm supposed to compute midpoint and provide it as the point. So initially, so there's the base position and the target position, which is to say there's the base position A. It's always going to be A. And this one is going to be the midpoint, right? So, because initially this is going to be B. Right? In fact, we can inline it, right? So we assume the midpoint to be B. We pass it off, and we get the new midpoint. And that is going to be the new B. So we pass it off, and we get the new midpoint. Did I say it seems like it's fair? And I could just go ahead and call here recurse midpoint, passing it pos x, pos y, and then next pos x, next pos y, and then 3, which is same as we've got here. We're going to go recurse midpoint, and we're going to pass it off op pos x, op pos y, and next op pos x, next op pos y, 3 recursions. I'd say it should do it. I'm hoping it does it. And it does it. That's great. Now if I say do 4, it should be slower. That's right. If I tell it recurse 5 times, it should be even slower. And if I tell it to recurse, say, 2 times, so even faster, it goes fast as fuck. And then if I tell it to only recurse 1 time, it's going to be pure speed. And that's it. And this is top speed. So it's nice because we know that there's top speed, and then there's like a probably at some point the midpoint is so small that the increase is like, imperceptible, I suppose. All right, so basically now I just have to parameterize that. What the teacher expected the speed to be. It's not going to be a float in my case. It's going to be, and initially it's going to be 1. Then here, instead of this, I'm going to pass it speed, the global variable. If I make, we get it fast as fuck. If I go into speed, I go into 2, it's not so fast. If I go on to 3, it's slower. If I go on to 4, it's a bit slower. If I go on to 5, it's a bit slower. And so on and so forth. Alrighty, so now I'd simply have to make a key callback, so pretty simple. Let's go down here, let's go mouse callback. I forgot what the signature had to be, so let me get rid of this, get rid of this, get rid of this. This was useful, this was also useful, and this was not useful, this was useful. This I've still got to read, this I've sort of read, but I got to read again. This was very useful, and yeah, whatever. Now, the mouse callback, GLFW callbacks. Input guide, all right. This guide introduces the input related, alrighty. For detail and specific function in this category, see input reference. I'm gonna need let's see. Set cursor pass, nope. Set key callback, set mouse button callback, that's the one. So I'm gonna need this one. The set mouse button callback. I mean, technically they're all on the same page. So say it's gonna be mouse button fund. It's the function. The function signature is supposed to be taking up a function pointer, returns void, and it takes up the window, the button, the action, and the modifiers. I'm only interested in the button and the action, so let's do that. So this is going to be a DLFW window. It's going to be the pointer. Then we got an in and in and an int. That is correct. Let's copy this. Let's go to this one's definition. Let's go ahead, do this, and take if. Wait a second. I'm gonna need first to specify that this is. I technically don't need the window, so let's just go action, and this is key. So I mean, no, it's the other way around. This is button, and this is action. So if action happens to be the mouse button, the action which was press. So if GLFW press, then we're gonna make a little switch with button, and we're gonna say, all right, was it a GLFW a mouse button? Which let's go ahead and take the input. If it's mouse button 1 and mouse button 2, I'm gonna go ahead and assume. Let's use these alias, which are more clear, clearer. Left is 1 and right is 2, but when I say left and right, the teacher's probably going to have an easier time. So let's go GLFW, mouse button left, so mouse button left. Why do I get the... There we go. Now, if it's a mouse button right, so if it's a left, it's going to speed up. So speed, we're going to add to speed. If it's the other way around, then we're going to subtract to speed. Then, well, we're going to first check, hey, is speed smaller than something? So I go speed, if speed is greater than 1, then we have that speed is supposed to go minus. But if not, well, false. or 0, or void pointer, or cast. Yeah, that's what I thought. Hey. Alrighty. You don't need this one, and we're good. So let's make and let's build. And now, wait a second, let me get my mouse because I'm using a touchpad. Except I can't get the mouse because, god damn it, I can't really get the mouse basically. Oh boy. Yes. Technically, left click, right click is 2 tabs on the yeah. So if I go like this, it doesn't. Yeah, I'm guessing this is, god damn it, I can't make it work because the touchpad is not detected. That's the unfortunate part. So yeah, there's that. Alrighty. Let me go ahead and make it and see if I have, there's some function for the touchpad. So set car mod, set Unicode character with modifiers callbacks to the mouse button to the cursor position. Joystick returns the values while axis on the specified joystick. Joystick, gamepad mapping. Not quite. And apparently, wait a second. I'm so dumb. I am oh so dumb. It's not that it doesn't recognize it, it's that I didn't even set it. Oh boy. Alright, so this is going to be the mouse callback. We're going to pass it our window, and we're going to pass it our mouse callback. Delete. Let's build. Slower, and slower. And that's nice. And it works. And I love it. And it works. Alrighty, it works. Now, I'm gonna document whatever is yet to be documented. And I'm gonna go ahead and replace the shared pointers for unique pointers because I only really use them as unique pointers. They're owned basically, but maybe I'm missing something, so I could be wrong. Then I'm gonna see about those floating point comparisons, and yeah, that's it. So that's documented. All right, all that is documented. This is documented as well. No need, and this needs documentation. So let's go ahead and do it. I think about it, it's a better idea if I call it iterate midpoint. It's an iteration, not a recursion. Alrighty, so it's done. Finally, it is done. It has been completed. Alrighty, so it works. And it seems to be correct. Now, time to change the unique pointers to the shared pointers to the unique pointers. Now that means we have to make unique. I'm just going to select all of the make shared and do it make unique, and that's it. And it should work. What the hell? Well, we got that one out of the way, but let me check out that everything works. Nice. Alrighty, I like it. And now I'm gonna have to change it so that it does better floating point comparisons, as in actual floating point comparisons, and not this faulty piece of crap I'm using. Px equals 0f. That is absolute madness. Because that doesn't change anything, right? Alrighty. Now, now, gotta read this page. Gotta read this page. So I'm gonna start from this very. Alright, this I think I read last night. I gotta read it again. Basic answers. Why don't my numbers 0.1 plus 0.2 add up to a nice round 0.3, and instead I get a weird result like 0.3 and a shit ton of zeros and a 4. Because generally computers use a format that cannot accurately represent a number, like a 1, like 0.1, 0.2, or 0.3. When the code is compiled or interpreted, your 0.1 is already rounded to the nearest number in that format, which results in a small rounding error even before the calculation happens. Why do computers use such a stupid system? It's not stupid, just different. Decimal numbers cannot accurately represent a number like 1/3. So you have to round to something like 0.33, so you don't expect 0.33. You don't expect 0.33 plus 0.33 plus 0.33 to add up to 1 either, do you? Of course not. Now, computers use binary numbers because they're faster at dealing with those, and because for most calculations, a tiny error in the 17th decimal place doesn't matter at all, since the numbers you work with aren't round, or that precise anyway. What can I do to avoid this problem? That depends on what kind of calculations you're doing. If you're needing your results to add up exactly, especially when you work with money, use a special decimal data type. If you just don't want to see all those extra decimal places, simply format your results rounded to a fixed number of decimal places. Wait a second. Whatever, if you have no decimal data type available, enter is to work with integers. For example, do money calculations entirely in cents. But this is more work and has some drawbacks. On using integers. While integer types are usually binary and by definition do not support fractions, they are exact, no rounding errors when converting from decimal integers, and can be used as a sort of poor man's decimal type by choosing an implicit fixed decimal point so that the smallest unit worked with can be represented as the integer 1. By choosing an implicit fixed decimal point so that the smallest unit you work with can be represented as the integer 1. In practical terms, this is often put as to handle money, store and calculate everything in cents and format only the output. Alright. I'm thinking maybe I don't need any of this. Let me set a breakpoint at line 113. No, line 115, and another one at line 122. If at no point at all in the program's execution do I ever enter there, then I can, number one, get rid of those two big if and else ifs at the start. And number two, I can get rid of the left, right, top, and bottom variations.
what's the name in C++? Enum types. No, it's not an enum type. It's one of the variants in the quadrant type enum. So if I no point do I enter them, I can get rid of it. But if I do, then I'm going to have to keep reading. So there is a point at which it's hit. Alright, yeah. There's a point at which it hits, so yeah, I'm going to need to do that. Let's disable all breakpoints. Let's continue execution. And let me quit. Alrighty. Well, if it does, then yeah, it's not so simple. Alrighty then. In that case, I'm going to have to keep reading. Either way, I should have continued reading anyway. It's always good to learn something new and make my programs better. This works, but has a number of severe drawbacks. It's more work and more opportunity for bugs to get it right, especially in regard to rounding modes. Integers have complete precision. Still, using decimal type, the limited precision decimal, basically the same as the binary floating point, except that the exponent is interpreted as base 10. Let me go back to basic answers. If you have no decimal data type available, an alternative is to work with integers. For example, demonic calculation is entirely in a sense, but this is more work and has some drawbacks. Now, why do other calculations like 0.1 and 0.4 work correctly? And in that case, result 0.5 can be represented exactly as a floating point number, and it's possible for rounding errors in the input numbers to cancel each other out. But that can't necessarily be relied upon. For example, when those two numbers were stored in differently sized floating point representations first, the rounding errors might not offset each other. In other cases, like 0.1 plus 0.3, the result isn't really 0.4, but close enough to 0.4 is the shortest number that is close. Wait a second, but close enough to 0.4 is the shortest number that is closer to the result than to any other floating point number. All right, for sure, like an infinitesimal approximation that is actually discretized. Fair. Many languages then display the number instead of converting the actual result back to the closest decimal fraction. So many languages then display the number instead of converting the actual result back to the closest decimal fraction. Fair. Alrighty. Let's go on to number formats or references. Documents that contain more in-depth information about topics covered on this website. Wait a second. Before getting onto this one, let me finish reading all of this. Front version of IEEE 754 standard, what every computer scientist should know about floating point arithmetic. Homepage of Will and Cahan. Architecture of the IEEE 754 standard. Lots of interesting links. Decimal arithmetic. FAQ. Comparing floating point numbers at Bruce Dawson's article, right? Tools to convert numbers between bases, including fractions. Float toy. Toggle individual bits to see what the effects on the value are. The visualization of IEEE 754, another bit toggling tool. So when you toggle this one, wow, that's a big wow. That's a big wow. My lord. Wow. Yep. The result of 0.1 and 0.2 in various programming languages. Nice. Yeah, I remember this page. I read about it some time ago. In C++, you get that. Well, let's go to binary fractions, how they work. As a programmer, you should be familiar with the concept of binary integers. For example, that is the representation of integers numbers as a series of bits. So we've got decimal, base 10. All right, makes sense. 1 times 10 to the power of 3 plus 3 times 10 to the power of 0. That is 1. That's 13 in base 10. And we got binary as well. So 1101, that is 8 plus 4 plus 1 makes 13. And then we have again 1 times 10. Yeah, all right, so that's a simplification. That's nice. This is how computers store integers internally and for fractional numbers in positional notation. What is positional notation? Oh, yeah, I remember. Yeah, I read about that some time ago. They do the same thing. Fair.
That makes complete sense. Problems. While they work the same in principle, binary fractions are different from decimal fractions in what numbers they can accurately represent with a given number of digits, and thus also in what numbers result in rounding errors. Specifically, binary can only represent those numbers as a finite fraction where the denominator is a power of 2. Unfortunately, this does not include most of the numbers that can be represented as a finite fraction in base 10, like 0.1. And this is how you already get a rounding error when you just write down a number like 0, 1 and run it through your interpreter or compiler. It's not as big as 380 and may be invisible because computers cut off after 23 or 52 binary digits rather than 4. Let me read that part. Specifically, binary can only represent those numbers as a finite fraction where the denominator is a power of 2. And the limited precision decimal type changes the power of 2, that is the denominator, to be a power of 10, right? I think I remember reading that. Unfortunately, this does not include most of the numbers that can be represented as a finite fraction in base 10, like 0.1. So when you consider base 2 as the denominator, you realize that 0.1 uses, we have 0.1, rounded to 4 digits is still 0.1, and so on and so forth. In base 2, 1 on 10 is 0.00011. And then 0.001, rounded to 4 digits, rounded value is a fraction, and the rounding error is 3 on 80, which is actually a lot. And 1/3 with base 10 is 1 on 30,000, which is a lot less. Specifically, binary can only represent those numbers as a finite fraction, where the denominator is a power of 2. Of course. Unfortunately, this does not include most of the numbers that can be represented as a finite fraction in base 10, like 0.1. And this is how you already get a rounding error. A rounding error when you just write down a number like 0.1 and run it through your interpreter or compiler. It's not as big as 3 on 80 and may be invisible because computers cut off after 23 or 52 binary digits rather than 4. Right. But the error is there and will cause problems eventually if you just ignore it. Why use binary? At the lowest level, computers are based on billions of electrical elements that have only 2 states, that is, low and high voltage. I mean, they have more than 2, but we only are interested in the low and high. The medium point of operation for a BJT transistor is not what we want. We always want it when it's either at the saturation point, I think it was, and at the... So basically when it's very near the x-axis, where the x-axis, I think it was intensity or voltage. I'm not quite sure. And the y-axis was indeed either involves intensity or voltage. You're only interested in those 2 points, where the voltage is incredibly small and the intensity is high, or the voltage is incredibly large and the intensity is near 0. Those are the only 2 states in which you're interested in. By interpreting these as 0 and 1, it's very easy to build circuits for storing binary numbers and doing calculations with them. While it's possible to simulate the behavior of decimal numbers with binary circuits as well, it's less efficient. If computers use decimal numbers internally, they'd have less memory and be slower at the same level of technology. Fair? Since the difference in behavior between binary and decimal numbers is not important for most applications, the logical choice is to build computers based on binary numbers and live with the fact that some extra care and effort are necessary for applications that require decimal-like behavior. What's that link? The exact types. Let me go back to floating point types, as that seems to be the subsequent section, and I would be jumping through it if I skipped it. Now, why floating point numbers are needed. Since computer memory is limited, you cannot store numbers with infinite precision, no matter whether you use binary fractions or decimal ones. At some point, you have to cut off. But how much accuracy is needed, and where is it needed? How many integers and how many fraction digits? To And when you're building a highway, it doesn't matter whether it's 10 meters or 10.0001 meters wide. Their measurements are probably not that accurate in the first place. To someone designing a microchip, 0.001 meters, 0.8 of a millimeter, is a huge difference. They'll never have to deal with a distance larger than 0.1 meters. A physicist needs to use the speed of light and Newton's gravitational constant together in the same calculation, which indeed require a massive precision. Alrighty. To satisfy the engineer and the chief designer, a number format has to provide accuracy for numbers at very different magnitudes. However, only relative accuracy is needed. To satisfy the physicist, it must be possible to do calculations that involve numbers with different magnitudes. Basically, having a fixed number of integer and fractional digits is not useful, and the solution is a format with a floating point. How floating point numbers work. The idea is to compose a number of two main parts, a significand that contains the number of digits, that is, negative significants represent negative numbers, alright, an exponent that says where the decimal or binary point is placed relative to the beginning of the significand. Negative exponents represent numbers that are very small, that is, close to 0. So an exponent that says where the decimal or binary point is placed relative to the beginning of the significand. Negative exponents represent numbers that are very small, that is close to 0, which is to say you move it to the right, you move it to the left of the significand, right? If the beginning of the significand is like an exponent with a 0, that is equal to 0, negative exponents thus mean that they go to the left, so they're very small and they're close to 0, I assume. Such a format satisfies all the requirements. It can represent numbers at wildly different magnitudes limited by the length of the exponent. It provides the same relative accuracy at all magnitudes limited by the length of the significand. It allows calculations across magnitudes. It can represent numbers at wildly different magnitudes limited by the length of the exponent. It provides the same relative accuracy at all magnitudes, limited by the length of the significand. Let me read that one. It can represent numbers at wildly different magnitudes, limited by the length of the exponent. Fair? It provides the same relative accuracy at all magnitudes, limited by the length of the significand, as the significand dictates the number of digits it's going to have. Alright? It allows calculations across magnitudes. That is, multiplying a very large and a very small number preserves the accuracy of both in the result. Alright? Decimal floating point numbers usually take the form of scientific notation, with an explicit point always between the first and second digits. The exponent is either written explicitly including the base, or an e is used to separate it from the significand. That is, significand is 1.5, exponent is 4. In this case, with scientific notation, we would say 1.5 times 10 to the power of 4. Why do they use the dot sign and not the cross sign? Like, the cross sign is actually used for this in scientific notation, but hey, maybe I'm wrong, and it's more often that you see the dot and not the cross. Well, it doesn't matter. Negative 2.01 has an exponent of 2. The significand is negative 2.01. That would mean that the significand is then multiplied by the exponent to that base. Alrighty. And so you end up with negative 200.1, the fixed point value. I see. The significand is an against some number. The exponent is that to which you multiply by 10. That to which you power 10 multiplied by the significand. And you end up with that really small number. Now, the standard. Nearly all hardware and programming languages use floating point numbers in the same binary formats, which are defined in the IE 754 standard. The usual formats are 32 or 64 bits in total length, but there's also 128 bits, right? I think Rust has 128 bits floating point type. IA 128 bits. Or it had at some point, or I'm confusing it with the
Rust decimal crate, which definitely has a 128-bit decimal type, but it is the limited precision decimal type. So it's like the IE 754, but the exponent is base 10, I think. Nearly all hardware and programming languages use floating point numbers in the same binary formats. No, the base of the exponent is 10, even though in binary is 2, I think. Nearly all hardware and programming languages use floating point numbers in the same binary formats for defining the IE 754 standard. The usual formats are 32 or 64 bits in total length. That is, for single precision floating point numbers, we get 4 bytes, significant bits 23 plus 1. These are the ones that we use in this subject, fundamentals of computer graphics, because we're using OpenGL 3.3 and GLSL only introduced support for double precision floating point numbers in the versions that came with packaged with OpenGL 4, but we're using OpenGL 3.3. Yeah, well, there's that. Note that there are some peculiarities. Let me read the table though. Single precision 32 bits. Fair. Significant bits means 23 plus 1, 1 being the sign. The exponent bits are 8. Oh god. And the smallest number is 1.2 times 10 to the power of minus 38, the largest being 3.2, 3.4 times to the power of 38. Double precision is 64, so you have 52 plus 1 sign, and the exponent bits there's 11 possible exponent bits, which is to say you can go from 10 to the power minus 308 to 10 to the power 308. So because it's 11 exponent bits, what's the largest number that you get with 11 bits? Well, with 4 bits, you can get 16. With 8 bits, you can get, I forgot, and you just have to add 3 to those. Yeah. But yeah, with 8 bits, you can get, well, no, with 8 bits, you can get 38. The largest number you can represent in 8 bits is 38. And so with 9 bits, that would be, so 1, 2, 4, 8, 16, 32, 64, 128. You would add 256 numbers, and then you would add 512 numbers, and this thing is not adding up, so it's probably not the way I think it is. If the exponent bits are 11, oh yeah, of course, I am so dumb. No, with 8 bits you don't get 38. With 8 bits you get from negative 38 to 38, which is 76 bits, right? No, it's 96. You get 96 bits. Wait a second. How many decimal numbers fit in 8 bits? On my calculator, bit length. Big integer? No. That's not what I need. God damn it, that's not what I need. My lord. Big count, 11. So, if I go now, I don't know, 32. You need 6 bits. Fair, so 0, 1, 2, 3. I mean, that's 1, 2, 4, 8. What the hell? This is not right. Whatever, it is what it is. It's in the range negative 38 to positive 38. That's it. Now, the actual bit sequence is the sign bit first, followed by the exponent, and finally the significant. Alrighty, so we get the sign, the 8 exponent bits, the exponent with a power that may be any number in the range that 8 bits offers, and then the other 23 significant bits, right? Yeah, that's right. Now, the actual exponent does not have a sign. Instead, an exponent bias is subtracted from it. My God. An exponent bias subtracted from it. So 127 for single and 1023 for double precision. This and the bit sequence allows floating point numbers to be compared and sorted correctly even when interpreting them as integers. Alright, so the exponent does not have a sign. Instead, an exponent bias is subtracted from it, so 127 for single and 1023 for double precision. That is, once you get the right exponent, you then subtract 127 to the resulting exponent, I assume. This and the bit sequence. Wait a second. Oh, so that's why I get a smaller range, because you then subtract 127 to it. It's 32, so 64. No, yeah, 32, 64, 128 to 156. Eventually, with 8 bits, you get something. So it's 4 bytes. So you get like what? 2000 million or so. Yeah. I mean, no, you get, what am I saying? 2000 million. It's not 2 billion. It's, yeah, it's 1 byte. 1 byte being 1,000 something. Yeah. This and the bit sequence allows floating point numbers to be compared and sorted correctly even when interpreting them as integers. Allows floating point numbers to be compared and sorted correctly even when interpreting them as integers. The most significant digit is omitted and assumed to be 1. Oh, except for subnormal numbers which are marked by an all-zero exponent and allow a number range beyond the smallest numbers given in the table above at the cost of precision. Let me reread that. The most significant digit is omitted, so we skip it altogether and we always assume it's 1 unless we are treating subnormal numbers. Subnormal numbers being those that are marked by an all-zero exponent, that is, in the exponent bits we have them all set to 0. And thus we allow a number range beyond the smallest numbers given in the table above at the cost of precision. So technically, if exponent bit is 0, we always end up multiplying by 1 the exponent. And so the significant, technically then, can use the bytes of the exponent, right? Right, that's what I thought. That makes a lot of sense. There are separate positive and negative and 0 values, differing in the sign bit where all other bits are 0. They must be considered equal even though their bit patterns are different. There are special positive and negative infinity values where the exponent is all negative 1 bits and the significand is all 0 bits. Wait a second. I didn't quite understand the previous line. There are separate positive and negative 0 values. Oh, so we have a positive 0 and a negative 0, which differ in the sign bit where all other bits are 0. These must be considered equal even though their bit patterns are different. Oh, that's nice to know. I mean, it's internal and we likely don't have to bother about it, but it is what it is. There are special positive and negative infinity values. Oh, where the exponent is all 1 bit, so we have the largest possible exponent that we represent, and then we subtract to it the exponent bias, 127 for single and 1022 for double precision, and the significand is all 8 bits. All 0 bits. These are the results of calculations where the positive range of the exponent is exceeded, or division of a regular number by 0. So let me read that last part. These are the results of calculations where the positive range of the exponent is exceeded, that is, calculations where the positive range of the exponent, that is, upon subtracting the exponent bias, we're getting
too large a number? No. We've already subtracted it from the divisor and the dividend in the calculation. And upon performing some calculation, no, it's not a division. It's some calculation where the resulting numbers, so the resulting floating point numbers exponent bits have surpassed the regular positive range. And that's where we go ahead and say, all right, exponent all bits, significant all 0 bits. All right, that's nice to know. Or if we perform division by 0, that's also really nice to know. There are special nutty number, or NaN, values where the exponent is all 1 bits, and the significand is not all 0 bits. So that's the difference between positive and negative infinity. The exponent is still all bits, but the significand is not all 0 bits. It's something else. These represent the result of various undefined calculations like multiplying 0 and infinity, any calculation involving a not a number value, or application-specific cases. Even bit-identical not a number values must not be considered equal, because they're like the edge cases, the undefined behavior in the C and C++ standards, and maybe other languages. All right, nice to know. If this seems too abstract and you want to see how specific values look in IE 754, try the floatoid or the IE 754 visualization or float exposed. I think I already went in here. The floatoid basically considers, if we consider our regular 32-bit persistent, the one we're working with in our application, you would see, a second, let me disconnect this, you would realize that we have, technically these are the exponent bits, these are the significant bits, except -1, and then this is the sign bit, right? Yeah, the sign bit, that's why it triggers it. Then we have the exponent bit, which we can trigger. And that's like the largest number we can represent, 2 to the power of 128, because that's 1, 2, 4, 8, 16, 32, 64, 128. Then these are all the exponents. The exponent bits, which are, technically, if you trigger them all, you should get the same number. God damn it. So if you get this massive number, you realize that it is, well, that is to the power of 0, 1, 2, 3, 4. Technically, if this is 0 and we already got a 1 here, this is 2 to the power of 22. And that's 2 to the power of 22 minus 1023, because it's the exponent minus the exponent bias. The exponent bias being 127. Oh wait, not 1023, minus 127, because it's a single precision floating point number. All right, nice. I like this. Now, let's go on to exact types. While binary floating point numbers are better for computers to work with and usually good enough for humans, sometimes they're just not appropriate. Sometimes the numbers really must add up to the last bit, and no technical excuses are acceptable. Usually when the calculations involve memory. Unfortunately, there is no dominating standard like IE 754 for this. The 2008 version and the standard of the standard added decimal types, which actually we treat right here, which is the limited precision decimal, but it is too recent to have seen widespread adoption. Even though we're already in 2025, about to go into 2026, apparently it's too recent. Wait, but then when was the initial version of IE 754 released? If 2008 seems too early, my man, the last supervision is 2019. What the hell? Gotta be a joke. So it supersedes, so the 2008 supersedes 1985. You have to be kidding me. you're expecting more than 25 years, so you want more than 30 years to go by until it's actually supposed to be accepted? Oh man, that's just crazy. Perform software emulation. You don't need it on the hardware. I mean, Rust does it on the software. Whatever. Each language or platform has its own solution, sometimes multiple different ones. For details, look at the language cheat sheets. It's very unfortunate that there's no C++ there, but I think C++ does have a decimal type, much in the same way it has a complex type. Unfortunately, now there are at least 3 fundamentally different kinds of such types. Limited precision decimal, basically the same as IE754 binary floating point, except that the exponent is interpreted as base 10. As a result, there are no unexpected rounding errors, although this kind of format is relatively compact and fast, but usually slower than binary formats. Arbitrary precision decimal, sometimes called big num. I also know there's a Rust trait for big num, and for small int. No, I think it was big int. Yeah, I'm not sure if it was for arbitrary precision decimals. I'm pretty confident it was for integers, but not so sure if it was about decimals. Now, this is similar to the limited precision type, but has the ability to increase the length of a significant, possibly also the exponent, as required. Oh, so it allocates more or less memory for those bits. Alright, that's nice. The downside is that there is some basic overhead, that is, memory and speed, to support this flexibility. And that the longer the significant gets, the more memory is needed and the slower all calculations become. Yeah, makes for a amount of sense. It can be very tempting to say, my calculation is important, so I use as much precision as possible. Yes, I'm assuming everybody would say that. Given their seriousness of how their work, they would. But in practice, the actual importance of precision at the 10,000th decimal digit quickly pales in comparison with the performance penalty required to support it. It can be very tempting to say, my calculation is important, so I need as much precision as possible. But in practice, the actual importance of precision, as at the 10,000th decimal digit, quickly pales in comparison with the performance penalty required to support it. That is, in practice, the actual importance of precision at the 10,000th decimal digit quickly pales in comparison with the performance penalty required to report. Oh yeah, sure, of course. Makes total sense. Symbolic calculations, the holy grail of exact calculations. That's like symbolic integration, which is so hard. Yeah. Achieved by writing a program that actually knows all the roots of math and represents data as symbols rather than imprecise rounded numbers. For example, 1/3 is actually a fraction 1 divided by 3. The square root of 2 is really the number that multiplied by itself is exactly 2. That is, the system understands math, basically, which is often not the case. Indeed, it's highly complex. Even transcendental numbers like Euler's number or pi are known together with their properties. That is, if Euler's number is powered to a complex number with imaginary part pi, we get -1, as in exactly -1. However, the symbolic math systems are complex, slow, and they require significant mathematical knowledge to use. They are invaluable tools for mathematicians, but not appropriate for most everyday programming tasks. And I'm pretty confident that also includes graphics programming with single precision floating point numbers. And even many mathematicians work on problems where imprecise numerical solutions are better because no symbolic solution is known. Indeed, much in the same way as numeric integration, only in numeric integration is actually has different goals than symbolic integration. Now, on using integers. While integers are usually binary and by definition do not support fractions, they are exact. That is, there's no rounding errors when converting from decimal integers. It can be used as a sort of poor man's decimal type by choosing an implicit fixed decimal point so that the smallest unit you can work with can represent as an integer 1. That is, by choosing an implicit fixed decimal point. Oh, so building your own abstraction, right? And storing each part separately with an implicit fixed decimal point that is part of likely your private implementation. In practical terms, this is often put as to handle money, store, and calculate everything in cents and format only the output. Or not even use an abstraction and assume you're using those types, and eventually just format the output.
This works, but has a number of severe drawbacks. It's more work and more opportunity for bugs to get it right, especially in regard to rounding modes. Integers have complete precision, but very limited range, and when they overflow, they usually wrap around silently. That is, the largest integer plus 1 becomes 0 for signed integers, or the negative value with the largest magnitude for signed. And that makes total sense, it's just underflow, overflow. This is just about the worst possible behavior when dealing with the money for obvious reasons. The implicit point, decimal point, is hard to change and inflexible in the storage. If you do dollars as cents, it's simply impossible to solve. The Bahraini dinar, which is like 1 dinar, 1,000, what the hell? What was Phil's? Let me see, what was Phil's? A person's father-in-law. A monetary unit of Iraq, Bahrain, Jordan, Kuwait, and Yemen, equal to 1/100th of a rial in Yemen and 1,000th of a dinar elsewhere. My God. And what is a fill in dollars? You either have to store the currency and handle the cents appropriately during display, or store the position of the decimal point with the data. Yeah, alright? The first step in implementing your own buggy, non-standard, limited precision decimal floating point format. Yeah. The number of subunits in currencies may change with time in the world. Due to inflation, deflation, some currencies may stop having subunits or add more subunits. If you store integers, you would need to migrate the already stored prices to the new format. This is a complete and total nightmare in an established system. Which is to say, using integers is not recommended. Do this only if there's literally no better alternative whatsoever. The better alternative being the exact types. Errors, rounding, comparison, which is the one I'm interested in. I'd say my computations work fine the way they do, so I'll just leave them this way, and yeah, that's it. Let me try out something. When I keep slowing it down, it never crashes, right? Nice. That's really nice. Well, if it never crashes, I have no reason whatsoever to ever, do anything else. We have finished the lab. Finally. Alrighty, we are done. I do wanna wait a second because, of course, the algorithm I use here, it's not mine, so I have to give reference. Alright, so,
And this is where I gotta give reference to the site where I got the algorithm, and yeah. Oh, sorry for that. Alrighty, so yeah. So I gave credit where I had to, where credit was due. I got the algorithm for the intersections from this page. All of this I can close because it's just UFW docs. This I already referenced. This is the tool I use to like find things out, basically. Can I save the canvas so that I can show it to the teacher if he wants to like see it? It'd be nice. So like, save to my computer. How did it save it as? Did it save it? Oh, it did. It did. Sorry. It's just that apparently yeah, it's there. Yeah. All right. So I'm gonna save the export, and I'm gonna also include it in the repo so that I can show the teacher how did I conclude what I ended up concluding. Um. All right. Then I also got the midpoint formula for this from this. All right. Oh, sorry. Then, oh yeah, I also have to reference the word that I got the midpoint from it. All right, now I'm gonna need this, and I'm gonna need to reference this. So there we go. There we go. So carry what is due. I got the midpoint formula there. I got the circle line intersection formula there. I saved this because I'm going to need to explain it to the teacher. This is really useful. This page is really useful, so I'm just going to, I already saved it. I don't think I have to reference this. It's like the unit circle. Everybody knows the unit circle. What can I say? Documentation from GLM. Basically, I'm just going to get rid of all this. And yeah, we're done. All right. So great British do. I got the midpoint from there. I got the circle line intersection from there. Alright, so I got the bill graph right there, and alrighty. Yeah, sure. Oh, I forgot about documenting the parameters on this one. So, yep, that should about do it. All of this is correct. I think I want to call it, instead of mouse callback, let's call it mouse button callback. Yeah. References correct and correct. Alright, nice. That all seems correct. Technically, I can also make the traverse graph no except, right? And I think so. So, yep, dare I say we can. Right? We are not really doing anything. Then tile get transform. So technically, I mean, there is no except, right? Or not. Could be, it's not. Oh, Lord. Alright, I'm gonna need GLM. No, my lord, no, fuck me. GLM. GLM. No, not, oh, come on. No, this is not what I need. My god, I need the G-Truck. The G-Truck GLM, not this GLM. Oh, I'm gonna have a stroke. Anyway, I'm gonna have to look up the forks. So this is gonna be on Insights. Forks. The fork with the highest stars is basically the one I need, which is G-Truck's OpenGL Mathematics. Now, translate, that's the one I need. I know it's in GLM, matrix transform, which is somewhere. So I'm just going to go ahead and check out GTC, matrix transform, and matrix transform INL, which I believe is the implementation. It basically includes all of those things. And in the matrix transform, it basically includes geometric, trigonometric, and matrix. Beautiful. Great. It includes matrix transform.http in ext. Alright, so I just have to go into, no, god damn it, ext, gotta go into matrix transform. So can I genuinely not see matrix transform with a T? There it is, matrix transform. It includes the constants, geometric, trigonometric, and the implementation is matrix transform.inl. So this one, what I wanted was to check whether GLM translate is not no except. So let's see. All right, so GLM translate is except. So it can jump. It can, yeah, basically. We can have issues. Point being, the issues are possible. Issues are possible. Alrighty, if it's no except, then indeed I can't make the traverse graph no except. It could be that it's rows, but we don't know for sure. Bill graph, though, I think that I can make no except. Oh no, it uses transformations. Yeah, neither. This one, no, because it calls no except false functions, so no good. This one, good question. Avoid frame buffer size callback. Oh wait, no, doesn't matter. Key callback. I mean, this one I'm sure. Am I though? Is this no except? It's nothing, right? Because it's C compatible. It's got a C compatible ABI. If the ABI is C compatible, then such thing as no except are useless because there's no such thing as an exception handler in C. So yeah, I'm gonna look at the documentation. So let's go GLFW docs. Pages. There we go. This is gonna be GLFW said window should close. So said window should close. You gotta be fucking kidding with me. GLFW said window should close. No such thing as whether it's no except or except. Fortunately, not much I can do about that one, so I'm just going to leave it no except false. Now here, this one I know for sure it's no except. So I'm just going to go ahead and do no except. Alrighty. This one I'm not sure because it calls GLM ortho and set matrix precision, which I don't know if itself calls U matrix for FV to set the projection, the projection uniform in the vertex and was it the vertex? Yeah, I think it was the vertex shader. That one's definitely no except. This type is alrighty. We've got that one. We've got the speed. We've got the projection matrix and the model matrix, and basically the extern of the VS source and FS source for the vertex shader and the fragment shader. This one is not going to get changed. So we have solved the problem. Let me compile again. So let me make clean, and then let me see. This works as expected. And that's nice. Alrighty, so it works. Now that it works, we can go ahead and, much to my unfortunate, move on to the next exercise, even though I've loved every second of this exercise. Alright, now, first of all, I'm going to need to go into my downloads, and I had a failed download right there, right? Yeah, Fundamentals of Computer Graphics from Anna's Archive. I don't condone piracy. There's that part. And there's that, Fundamentals of Computers, Fundamentals. And there's also the, what was that one? Yeah, the double GeoGebra export. So there's the GeoGebra export, which I'm going to need. And the unit circle that I downloaded, and I can see with Chafe. Nice. Alright, so let me copy GeoGebra, the GeoGebra export that I made, onto my university folder. So this is going to be Fundamentals of Computer Graphics, the lab, my personal work, and yeah, I'll just copy it there. So yeah, let's copy that. We're good. The status is that we have a few things, but everything should be alright. So let me get the status again. We got the export, we got the lab, we got the source lab 2. Nice. Everything's good. Now let me rename real quick. Let me check out real quick my source lab. Let me check all the other problems in this lab, the other 3 problems. Yeah, I think there were some conventions that I didn't quite keep, as in my coding style. Then I also have to check out the libraries that I'm using, the ones that are, well, custom built, that is Fig models and Fig shader utils. And yeah, that should about do it. Now, the next thing is going to be, well, after this we just have Unity in the lab, so yeah, worthless garbage, basically. I'm gonna move on to, yeah, I'm gonna rename the files. So MV is gonna be problem 3 is gonna will go back to being problem 3 and not problem 3 back. Source lab 2 problem 2 is gonna go back to being problem 2. Problem 1 is gonna go back to being problem 1, and I'm gonna check out lab 1. Alright, that's nice. Everything is nicely documented. I think I can make this, no, I can't make this no expect, and I can neither make that no accept. I can stop separating this, doesn't matter. I do terminate on both of those, which I have to. Other than that, I do want to rename this to frame buffer size callback, as I did in the problem 4. This is going to be key callback, so key callback. Next thing is going to be yep, we got that. We got that. Oh, I forgot. In in the no in the frame buffer callback. No, it wasn't this one. It was that one. It's also out because we write onto it. So, I mean, it's only really in, right? It's only really out because we're only changing the window. So we set the window should close. We use a setter, but we never really, yeah. It's only an out. Yeah. I mean, no, it's in and out because it's setting that this specific window should be closed, so it's providing data about which window we should close, and it's also modifying itself, so it's in out. Oh yeah. It's in out, in out, in out. Alrighty. Alrighty. And so we've got the button, the action. That's just about to do it. Now key callback in this one. Let's consider that. And so on and so forth, whatever. I do the same thing there, whatever, who cares. We've got a display, we've got everything else there. It got the fake translate. Which gets us to GLM4. Yes, I have to change those values to explicitly floating point. I mean, there's no need to, but yeah. So no, I'm going to select any digits except those that are followed. So that's supposed to go in here. All right, I think I got it wrong. All right, now I got the regular expression one. Let me check out the regex syntax in the Rust regex engine. A character class matching any character except that one. All right, yeah. What I need is a character class matching any digit except another character class. God damn it. I need a character class matching any digit except the... Oh, Lord. I need a character class matching any digit except a character class that matches some mat 4 and some digits. What the hell? I got it wrong. Matching any character except Y and Z. What the hell? Alright. What if instead I just limit it to this and I match digits except vec digits. So except vec digits. What the fuck is this shit? Oh Lord. Why does it match the bracket? Why does it match the character that goes after the digit? My lord. God. What if I match just 0 and 1? There we go. What if I match again 0 and 1? Zero and 1. By the way, I can make all of these functions inline. Yep, I can. So let's go ahead and make them inline. Yep. Let's take start of the line, GLM. There we go. And now they're in line. Nice. Alrighty. Dare I say, seems good enough. Let's move on to problem 2. There was something I missed. Wait, what? What the hell? Why would I possibly want to use matrix transform here? I never really need a matrix transform, though. Like, literally, I never need it. I make the transforms myself. Yep. This header file is not needed. And that should do it. Now, I am thinking I could replace the trig functions for GLM's trig functions as well. Provided by, what the hell? No, it's provided by include GLM trig. It was there. No, not that one. The manual. No, the API reference. Trig. And that's where they're defined, right? Yeah. So GLM costs and so on and so forth, you know. You know the drill. Yep. Same applies here. It's not an ends, but whatever. You didn't get it right, basically. The LSP didn't get it right, so or something. So those are the ones I changed. Sure. Problem 2 uses scalar constants and matrix transform, then makes mat 4 by 4. ortho is in what? What? To use ortho as I use it here, I need to include what the hell? But it says it's included, oh, in matrix clip space. But like, if you look at the manual, it says something else though. Like literally, if I look for ortho, it says use GTC transform. No, it says projection measure, but it doesn't mention it's in there. All right. And it says it's in matrix transform, so I suppose I'm just gonna leave it in matrix transform. GL ortho is in. It's in GLM ortho is like in Yan, right? I mean, yeah, it's in GHEC matrix transform, so there's nothing wrong with that. Yeah, all right. So same as before. Let me rename this to frame buffer size callback. So frame buffer size callback and no, Lord, no. Key callback. I can't really make it that way, and there's no need to make this inline in both the definition and that, yeah. I call terminate every single time we have issues, which is, yep, there and there. Fair enough. And that should about do it, right? I use pi, negative pi, and so on and so forth, which seems fair. There's some numbers there I don't quite. And also this one's, let me select digit. This is supposed to be that, and this is supposed to be that. Let me select 0 or 1. That is correct as well. And seeing how it all seems to be correct, it's correct. Alrighty. Boy, why? Let me take out problem 3 real quick. Gotta get going already. Yeah, I'll take it out later on. I'm gonna leave myself a bit of a little wee break. And this is the end of the stream.